Welcome back to another video to create a machine learning bot to play board games. This is our fourth video, and in the first three, we have focused on creating a game board for the Tic Tac Toe. And so we first created a board where you can play one another, okay? And then we created a random bot, right? Where we can play against this random bot, right? So when you play as a human person, the computer will be able to respond using the random moves. Okay, so this doesn't really show much intelligence, but it is our first step to at least observe what computers can do, right, in response to our moves, right? But it doesn't really learn from this process. So in today's video, we are going to start the most exciting part of this series of videos, which is to create something that is capable of learning from mistakes, from success, okay? And so let me talk about what I'm going to do today, okay? And so because of the complexity of the code so far, in today's lecture, I'm going to create another notebook, okay? So we have been on this tic-tac-toe Jupyter notebook, but today I'm creating this new notebook. So feel free to, click on this plus button to create a new notebook, okay? And what I'm going to do first, before we get into the intelligent, this machine learning module, to learn to play the tic-tac-toe game, I'm going to do a couple of things on the logistics side. The first thing is to do some code reorganization because we continue to grow the code and we need better modules to organize these codes. And so what I'm going to do here is to create two Python modules, very simple Python files. One is called game.py, and put all game related, game board and rule based functions into the game.py. And then the other file is the bots.py. So we're going to put the random bot in there, and then we're also going to create the new bot, which is going to be a reinforcement learning module in there as well. And then we're going to call those, import those functions and classes into this current machine learning notebook. Okay, so this is the first part. And then the second part is a bug fix, okay? So, which is regarding the check win function. Because when we check win in the current code, what it does is only to check whether three cells in a row, whether vertical or horizontal or diagonal, are the same. But one thing I failed to check is that the cell value cannot be, quote space quote, or it has to be either X or O, right, to be a winner. Otherwise, there's no winner. So there is one more condition we need to add in there. So, but let's first start with the code reorganization and then do the bug fix. And then after that, I will talk about reinforcement learning, and we can implement this method together. So first thing is to right click on the panel here and new a file. And I'm going to call this file game.py. Okay, so this is the first thing. And game.py is going to have the code from our previous tic-tac-toe notebook, and everything within this cell for the code. So if you go back to your class for tic-tac-toe, just copy. You can Command A or Control A, and then Command C or Control C to copy. And then we are going to paste into this game.py. Okay, just put them in here. Actually, I'm not going to run at the end, so remove the last two pieces of code in case you have them. Okay, so in this piece of code, what we need to have is simply the class for Tic Tac Toe. Okay, we only need the Tic Tac Toe class. Save it. Okay, this is the first part. And then let's also new another file. Okay, and call it bots.py. These are Python files, and these are going to be Python modules that we are going to import into Notebook. So they have to be .py extension. Okay, so if you open it, for now it's empty, but now what I'm going to do is go back again to the original notebook, the notebook that we have been working on in the last couple of videos, and now go to the random bot module, and then copy the code and then paste the code into this bots.py. Okay, so that's all we need at this point, okay, for this code reorganization. Now there is one bug that I need to fix in the game.py. Okay, and the problem is with the let me hide this part of the window. The problem is really with the check win function. Okay, in the check win function, actually I already fixed it. Previously we did not have this part of code. Okay, previously we only had this condition to check whether the board 0, 0 is to 1, 1 is equal to 1, 1, and 1, 1 is equal to 2, 2. Okay, this is to check the diagonal line, but we also need to check not only they should be equal, but they also should not be equal to an empty. Okay, it should be taken, it should be either an X or O, or another way to say is that it should not be equal to quote space quote. Okay, so there are quite a few conditions that you need to add in here. So for the first condition, to check one diagonal line, and then for another condition to check another diagonal in another direction. Okay, you also need to check self.board 1, 1 is not equal to empty. Okay, and then add an end. Okay, so this part is what you need to add in the code, okay, to fix the issue. And then to check horizontal lines, we also need to add this condition. Okay, so because we check for I, right, we check each row with the index I, so we also need to make sure that each cell that we compare, each row, the cell should not be equal to quote space quote. Okay, so this is to check the rows, and the same also to check the columns. Again, you should add this self.board and then 0j not equal to quote space quote, and then also add this n as part of the condition. Okay, so this will fix the bug here, and perhaps some of you have already figured out this issue, and so this is a bug fix. So with this, I think we are good with the game.py and the bots.py. Okay, now currently in the bots.py we only have the random bot. Now we need to work on a machine learning module, okay, so that we can go beyond random moves, right? So we can create something that can actually learn from failure and success to make a move better, to make a better move, or make a kind of a, how do you say it, the more educated move, right? So let's talk about reinforcement learning. And this is actually quite a simple learning method that has been studied for many, many years and have been used in so many different applications, including what is really popular today, ChatGPT. But in this application, I'm going to use a very basic reinforcement learning method called Q learning, and I have discussed this method extensively in the link YouTube video here. Okay, so in this video, which I posted, I discussed the concepts and the ideas behind reinforcement learning. So for those of you who want to get into the method, check the video out. Okay, but here I would like to touch on a few key ideas applicable to the Tic Tac Toe game. Okay, so let's think about Tic Tac Toe and how a bot can play on the Tic Tac Toe and learn from it. Okay, so what a reinforcement learning bot is going to do is that it needs to monitor the entire situation, right, the state of the game. And if you think about the different possible states, think about tic-tac-toe having 3 by 3, right? It's a grid, and then for each cell on the grid, there are 3 different options, either X, right, or O, or empty, right? So there are 3 choices, 3 options, okay, and then it's a 3 by 3, which has 9 cells, right? So it's 3 to the 9th order, okay? And so in the end, you will have almost 20,000 permutations, okay? So there are potentially 20,000 different states, so to speak, okay? The state is really a term, an important term of the reinforcement learning, okay? They're just different situations that you have to encounter in the game, okay? And then, so you monitor the situation, and then based on the situation, you want to make a prediction of what would be a better move, right? So you can, of course, at the beginning, you don't know what to do, and the bot will perhaps just randomly select, just like what the random bot would do, right? So it will make a random move, right? And that is called exploration. So at the beginning, the bot will explore, okay, just make a random move and then learn from it, okay? So there will be an option to determine how much exploration, like the probability for the bot to learn by making random moves, right? So there is the exploration. But there is also the other part. Aside from exploration, there is exploitation, which is to make the move based on the past rewards or penalties. Okay, and so I will talk about the penalty a bit later. But each move, think about each move. When you make the move, normally the next turn is for the other player to play. And perhaps there is no immediate reward or penalty because the winner, you don't have a winner until perhaps a few steps further. So there perhaps no immediate reward or penalty, right? If there is no winner yet. But in the end, there might be a winner, okay? And if there is a winner, there will be a penalty, right? So if, let's say, the bot plays this move and it wins, there will be a reward. And you can say this will to be 1 or 10 points or 100 points, right? So it's a reward. But what if the bot moves and then the other player makes another move and that player wins? That means the move that this bot has made actually has led to a loss, right? And so in that case, the last move by the bot will receive a penalty, which is minus, right? So a positive score for a word and a negative score for as a penalty, okay? And so this is one game, and you can repeat this game again and again and again, right? So that the bot will accumulate knowledge about in what situations it will lose and in what situations it will get awarded. Okay, now when I talk about this last point, this point 4, right? Uh, it feels like only the last move will be awarded or penalized. But in fact, in reinforcement learning, it's more than just the last move that will be rewarded, right? So let me explain why. Because when you think about the moves on the board, you can think about one move lead to another, right? So when you make a move, it changes the state or the permutation of the board. And so you make this move, you change the permutation to another state. And so let's say, okay, you move 1, and then the other player will take their turn and play another move. And then you can move your move 2, which is another move, and then move 3. Perhaps at move 3, you have a win. Okay, so this move 3, given the particular state of the board, will be rewarded. Okay, so move 3 will be rewarded. But in reinforcement learning, there is also a part of the algorithm which, when we implement that specific algorithm, you will see there is a discount reward that will be propagated back to the other moves. So if you already have a move, you have a reward for move 3. Later, when we repeat the computation, and move 3, for example, receives 1 point, okay, for the win. And if the discount is 90%, then move 2 actually will receive 9.9 from that same reward. And then likewise, move 1, okay, which is 2 degrees apart from move 2, will receive 0.9 times 0.9, which is about 0.81. Okay, so so even though the final move carries the most importance and gets the most reward, the other steps, the previous steps leading to this win will also receive some award for the ultimate win. Okay, so this is the idea. For penalty, it will happen likewise. Okay, so a penalty for the last step will also be propagated to the second last step, and then to the third last step, and so forth. Okay, and so in the end, the bot will be able to learn actually the entire chain leading to a win. So in the end, we'll have a chance to play with the reinforcement bot and hopefully coach it to learn how to play this game better. But obviously, it's going to be time consuming if we as humans have to coach the bot step by step. And so a better approach is actually to create 2 bots and let them play against one another, right? And learn from the experience. And we can let the bots perhaps, play 1,000 games, 10,000, 100,000 games, and see how much they can learn from it. Okay, and we will see the improvement. So let's get started with that implementation. Okay, so first thing I would like to do is simply to make sure the previous code from the code reorganization will continue to work. Okay, so one thing I would like to do here as part of the reorganization. So I already have the notes here. You don't have to recreate a note, but as long as you recreate another empty notebook, you can follow me here. Okay, so the first part is we already have the game.py with the Tic Tac Toe class, and then we have the bots with the random bot class. Okay, so let's import these modules, and hopefully we can make them work. Okay, just to test this code organization actually works. Okay, so we are going to import Tic Tac Toe from game. Okay, and then we are also going to from bots import the random bot, right? These are what we have done in the past couple of videos, and then we are going to create an instance of the Tic Tac Toe game, and then we are also going to create an instance of the random bot. Okay, this is just for testing before we proceed to create a new bot. Okay, and then we are going to set the game bot to bot. Okay, so we create this bot out of the random bot. Okay, and set this bot as the bot to play the game. And now what we can do is to show the game. Okay, so I believe it's display, right? So let's run this piece of code. Okay, so we connect the game and the bot together, and now we can play the game against the random bot, which is playing everything randomly. It could, you know, have good moves, but oftentimes it will just play random and doesn't really learn anything from playing the game. Okay, so the next, now that the passcode is working, let's go to the next step, which is to create reinforcement learning. Okay, so let me get my notes, and what I'm going to do is go back to the bots.py and create a class for the reinforcement learning. So I'm going to create RL bot here. Okay, and this is really a bot capable of reinforcement learning for playing Tic Tac Toe. Okay, and the first function is going to be the constructor. Okay, double underscore init double underscore. There are a number of parameters that we need to pass to this bot. Similar to the random bot, we have the game and player, so we're going to repeat that as well. Okay, so game and player, and and there are also a number of parameters that we can pass to the reinforcement learning. Okay, there are three particular parameters, and the first one being the learning rate. Okay, so there will be a learning rate, and we can set a default value here or not. Let's just set any random value here, and later we'll figure out what values will actually make sense, and based on intuition, and hopefully also impact the rate at which the machine learning module will be able to learn and get trained. Okay, so this is our constructor, and the first thing is to set the game to self.game. Okay, so we keep track of which game the bot is playing, and then which player, okay, X or O, it is playing. And then as part of the reinforcement learning, as I said, I'm implementing a specific algorithm called Q-learning. And as part of the Q-learning method, there is a so-called Q-table. Okay, so Q-table is basically a dictionary. You can think of it as a matrix or dictionary that's keeping track of the values, the scores for each state and action. Okay, so because it's going to be, in our case, we're going to implement this as a dictionary. So put a pair of curly brackets in there because we want to be able to quickly look up a state and for its value. Okay, so let's implement a qtable as a dictionary, and then we are going to also set the parameters. Now instead of setting the parameters here, I'm also going to create another function just to set the parameters, because this function will be reused. Okay, and what I'm going to do is that I'm going to copy and paste these three parameters here. Okay, so the learning rate, discount factor, and exploration. Okay, I'm going to explain further what these three mean. Okay, but for now, just follow me, and we simply want to set the values. Okay, so the first one is the learning rate. Okay, and then the second one is the discount factor. Okay, and then the third is the exploration rate. Okay, we just pass these values to the three parameters. Now in the constructor init function here, that's also called self.set parameters, params, and then pass these three values, okay, from the constructor. Okay, okay, so this is the constructor, and then this is another function which we will reuse to set the parameters. Let's also define a function to change game. Now the reason for this function is so that we can switch the bots to play different games. Why do we need this? Think about this. So at one point we're going to train these bots, and at the beginning we can create two bots and let them play one game, okay, repeatedly. Okay, and then later we're going to reconstruct another game so that we can play one of the bots, right? So once a bot is trained, we would like it to switch to a game so that we can play it. Okay, so that's the idea. And so this is very simple. Just change the self.game to this new game, just in case we need to switch the game. Okay, now we are getting into the part where we do want to keep track of the state of the board. Okay, so let's assume we have a board and we want to kind of see what kind of state. Okay, so because the game you know, is already can be associated with the bot, and bot knows what game it's playing. Okay, so ultimately the game comes with the memory about what's going on during the game, which is about the game board memory, the 3x3 grid with X, O, and empty values in there. Okay, so in Q learning, in reinforcement learning, we need to identify each unique state. Okay, and so let's create this function to get the state. Okay, so let's get the current state of the board. Okay, which is a two-dimensional, right, array. Okay, and of X, O, and empty values, right? So define get state self, and then there has to be a board passed to it. Now because of existing implementations to help us kind of make this code more efficient, I would like to use a package in Python that is very popular for data analytics, okay, which is NumPy. Okay, so so import at the top, please import numpy as np. And so for this board, originally we created the board as a regular array in Python, but here I would actually like to use the np array, which is numpy implementation of an array. It comes with very nice features for us to easily manipulate those arrays, okay, for our objectives. Okay, so in this case, if it's an np array of the board, okay, think about, we only need to return a unique value representing each state. Okay, so here I'm going to just go with a very simple implementation of string board dot reshape -1. Okay, this may look confusing. Actually, let me do an experiment somewhere. Okay, so allow me to go back to this machine learning but. Okay, and what I'm going to do is insert a cell here. I'm going to just play with this and see what values you can get from that kind of, because I do want to show you what this means. Okay, so let's go back here and let me go to the part of experiment that I would like to do here. Okay, so there are a couple of things. Okay, so when we have the game up here, right? Whenever this game is played, the board will be changed. So we can take a look at the board. Game.board, if you take a look, right? This array, two-dimensional array, really represents the what is going on, right, on the board. So first row, second row, right, and then the third row. These corresponds to what you see on the visualization. Now, I would like to use the np array, right? So let's see if I use np array to convert this game board into an np array, right? Now, it doesn't allow me to show it directly, but let me try one thing. Let me convert this to, for example, np board. Oh, I need to let me import numpy as np here. Okay, so first import numpy as np, and then convert this game.board into a numpy array. And then if you do so np okay, so this still looks similar, okay, but it's a numpy array. Now if you do this np board dot reshape, this is going to original, right now it's a two-dimensional 3x3 grid. If you reshape it, this is actually going to reduce the dimensionality and make it flat. Okay, so see, originally it was a 3x3 matrix. Now it's a kind of a one list of 9 elements corresponding to what's on the board. And then if I use string, okay, to concatenate all the elements together as one string, this is what I get. Okay, so this becomes a unique value, just one string, to represent the unique state of the game. Okay, so while we are here, there is another thing I would like to show you. Okay, so if you look at so now on this you see with this reshape, I'm able to flatten the two-dimensional array into one-dimensional one. Now a second thing I would like to do is just to show you quickly this and bear with me. So again, I'm going to use this np function to search for something like, so this np where is to search for the elements or the cells containing the value of space, which is unoccupied, right, cell. and then zip and convert that to a list. Okay, so let's see what it does. Okay, so when you do that, this is actually going to search for all the empty space and give you the index of it. Okay, so what you do here is to get the index. Remember, if you remember our index system, the rows have indexes from 0, 1, 2, and the columns also 0, 1, 2, right? So this is to give you the index of the, let me see if I can, I actually don't have the pen, but the first empty cell available action is here at 0, 1, right? 0, 1 is the first row and second column. Okay, another available action or cell is at 1, 0, which is the second row and first column. Okay, and then if you look further, there is also 2, 0, which is the third row and first column, and then 2, 1, which is the third row and second column. Okay, so this list is a list of the index, okay, for each available cell, which is the list of available actions one can play, right? So these will be useful when we actually get into the code, okay? But I just wanted to show you these first before we get there, so it makes sense. Okay, so this board or reshape is going to flatten the two-dimensional array, the board, into one-dimensional, and to create a unique value, okay, with this string function, just to concatenate the values together as a unique value. Okay, so this is the get state. Okay, now we know we can get this current unique state of a board. We can also, as we discussed, we can actually figure out the index for the available empty cells, right? So the next function we are going to define is to get available actions for empty cells, right? Because these are the cells that the bot can play, right? According to the rule. So let's define get eval actions self.board, right? And now previously, if you go back to the code here, okay, let's copy the code here actually. Okay, there's a list zip. So what we're going to do is, and of course the parameter is called board, okay, but we'll assume it's going to be a numpy board, okay, and so these are all available actions in 2D, okay, two-dimensional, right, because they are, again, if you switch back, there are two values in each cell, okay. Now I would prefer to have a 1D cell, so we can flatten this part of the code out, okay. So what I would like to do is, again, to use some numpy function, okay. Maybe I should show you here before I show you. So remember, this is one-dimensional, and if I assign this, for example, to something called index 2D, okay, so I assign this to index 2D, and I print those. Index 2D is index 2D. Now I'm going to take the index 2D and put it as part of, let me reconstruct this, okay, so I'm going to create a array, okay, based on this numpy function, okay. So this is Ravel multi-index, and so index based on index 2D, okay, wait, actually based on so available based on each cell or action. Let me call it act, right? And original is 3 by 3. The script is 3 by 3, and for act in index 2D. Okay, so in this case, you can ravel the multi-dimensional index or two-dimensional index into a one-dimensional one. Okay, so that's what you get. Okay, so once you have done that, I will run it. Okay, let's double check index for index 2D. I think I'm missing a parenthesis here. Run it again, and now that's output index 1D. Okay, it becomes 1, 3, 6, 7. What does it mean? Okay, so it actually goes through each row first and then follow the columns. So the first row, first column is 0, and then this one is 1, and then 2, 3, 4, 5, 6, 7, 8. And so 1 is the first row, second column, and then 3 is the second row, first column. 3, 4, 5, 6. 6 is another available action, and 7. Okay, so they are still the same index, but now instead of having two numbers, we have one number. Okay, so let's copy this code over, and we can kind of reuse it in the bots. Okay, so I'm going to call it actions 1D, and I'm going to ravel the actions 2D into the 1D. Okay, and then in the end, I'm going to return this actions 1D. So I'm going to return the one list of the indexes for the available actions. For the cells that are still empty, that can be played. Okay, so this is the available actions. Now, let me also create a relative function based on these available actions, because when we know what available actions are, we can also determine if there is no available action, okay, and there's a winner yet, then there's a draw, right? So we can at least determine whether there's a winner and there's a draw, and this is very important during the training process, so we know the game has come to an end and we need to restart the game for another game of training, right? So let's create check if the board is full and a draw. Okay, potentially a draw. And so let's define this board is full, self board. Again, you pass the board to it, and then we can simply return if the length of the get available actions, okay, board is equal to 0. Okay, so we call I missed something, self.get available actions. Okay, so self.get available actions board is going to call the function up here, okay, to see how many available, to return the list of available actions, and then we can determine whether the list is empty or not. Okay, if this list, the length of the list is empty, that means there is no available option, so obviously it is true that the game, the board is full. Okay, so this is the function. And then now we come to really some of the most important functions in the Q-learning. Okay, so we now know the state, and we now know the available actions, right? So we can perform a selection of an action. Okay, so let's create a function to pick an action or move, right? Given a state and available actions. Okay, so let's define the function select action self given a state and available actions. Okay, we can pick an action. Now, how do we pick an action? Okay, let's talk about one of the parameters. Remember just now we talked about this exploration rate. Exploration rate is really the proportion to determine when the bot will explore versus exploit. So another way to do it is like this. For example, exploration, if it's at 0.1 or 10%, that means 10% of all moves will be random. And then 10% is random, and then 90% will be based on what has been learned. Okay, so this exploration rate is really the rate for the random moves. Okay, so to do that, one thing we can do is, I think we're going to use a random function. Let me double check. Yeah, we do have a random, import the random there, so we are good. So if we can call this actually mp random.random, okay. So using the random function, we can just create a random number. And if this random number is less than the exploration rate, okay, the random number is always going to be from 0 to 1, okay. So if the number is less than the exploration rate, which for example can be 10%, okay, then we are going to just pick a random action, okay. So how can we pick a random action? We can use action equal to mp.random choice, and then based on the available actions. Okay, so out of all available actions, we are going to pick just one, okay, randomly. Okay, but if the value that we pick is or randomly generated is greater than this exploration rate, that means we are going to actually predict the move based on what has been learned. Okay, and so the learning is really based on Q table, so we need to get the Q values. Oh, there's one thing I missed. I think I still have yet to implement the method for get Q values. Okay, so let me add the new function under get state. Okay, let's implement the function for get Q values. Okay, and so each Q value or list of Q values are associated with a state. Okay, so the state has to be given. Okay, so get Q values for a given state. Okay, and so now at the very beginning, if the Q table, when the bot is just constructed, there's nothing in the Q table, right? So there's a chance that the state is not in self.Q table, right? Remember, we initiate the Q table here as an empty dictionary, so chances are there's nothing in there. Okay, so if nothing or the state does not appear in the Q table yet, let's just populate the Q values for the state with 0 values. Okay, so for the Q table state, okay, and we are going to populate that with 9 values. Okay, so so these are, so there are different states, and for each state, think about, okay, given a state, especially at the beginning, the state of all empty cells, there are 9 possible moves. Okay, so the reason that we have 9 is that for each state there are up to 9 moves. Okay, so these are all potential moves. Okay, and we need to keep track of the score associated with each move based on that state. Okay, so hope this makes sense. And then we are going to return the the Q table associated with the state. Okay, so if the state is not there yet, we are going to initially will be all 0 values. If the state has already been there, what we return is what has been kind of learned and calculated values for the Q table for the state. Okay, so that is get Q values. And we are going to rely on the Q values to determine what we are going to move, right, for the bud. Okay, so we are going to get Q values from self.get Q values state. Okay, and then we are going to look at all available Q values. Okay, which is the Q values. These Q values are based on, think about the Q values, 9 values, right? First row has 3, second row and third row, and it follows the order 1, 2, 3, 4, 5, 6, 7, 8, 9, or I should say 0, starting 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So these are the indexes for each cell. Now, it doesn't mean all the cells are available, right? Remember, as part of this function, there are available actions. And based on our previous discussion, these available actions are the indexes, okay, containing which cell, right, is still available, is still empty, that can be played. And so we are going to pass these available actions to it, right, so that we can single out those values, those Q values that are still available. Okay, and so these are available Q values, and then we are going to find out from these available Q values which one has been rewarded the most. Okay, these available actions in the past they have been played, and so we are going to find out which one has received the most award in the past. So in NumPy there is this arg max function. Okay, so based on the available Q values, we're going to use this argument max function to find out which action has the maximum reward or has the maximum score based on the past learning. And then this is whichever has the highest score is going to be our best action index. Okay, and in the end, our action is going to be based on available actions and then pass this best action index. Okay, if the best action is has the index 3, then we put the 3 in so that we can get whatever action it is there. Okay, so this will give us the action that we need, and then we are going to return the action. Okay, so the action can come from 2 situations. One is it's a random. Okay, so random move. Okay, or best move based on past learning, best Q value. Okay, so 2 possible values that you can get. Okay, so that is the selection. Okay, Now, based on the selection, there will also be rewards, okay? And the rewards or penalties are what motivate the bot to learn. Because think about this, there is argument max, okay? So we want to find out the best action that we select is based on whatever the score associated with that action. So how are these scores updated, okay? And so we are going to create a function to actually update the Q values, okay, based on the old state. And I will explain what they are: reward, action, reward, and new state, okay? And so we are going to update Q values for old state, okay? And then from the old state, if you take certain action, it's going to lead to the new state, okay? And in the end, it will come with certain reward, and if it's positive, it's reward, or if it's negative, it's actually penalty, okay? So this reward can be positive or negative depending. It's in fact a reward or a penalty. Like if you win, it's a reward. If you lose, it's a penalty, okay? And so how do we update the values? Okay, so the Q value is really based on condition of the current state, which is the old state, right? So the old state is like, okay, we have all these different X and O on the board, and then I'm going to make a move and mark another cell with perhaps X, right? That is my action. If I pick a cell and mark X on it, this is my action, which changes the state, right? That's why there's a new state. When you make a move, you change the state, change the situation on the board, okay? And so it will come with certain reward. So we need to incorporate all these parameters in here, okay? And so with the old state, they are all Q values, okay, associated with that current or old state, okay? And we're going to get Q values for the old state, okay? Now you can imagine there are going to be Q values for the new state as well, right? And so we get the old Q values and new Q values. Now for the old Q values, right? Remember, out of the Q values for the old state, these are associated with possible actions based on the old state. Like given the state, there are still these available actions that you can play. And so there is an action associated with each Q value for that old state, okay? And because currently we want to reward this particular action for that particular old state, okay? And so we need to use this formula so that we make sure we update the correct state and the correct action, okay? Because if the state is different, even you perform the same action, is actually the result can be different, right? You perform an action based on that situation. So we want to reward the action for that specific situation, so to speak, okay? And so how do we update? We are going to use the existing value. So because we are only going to update, it's going to totally change the value. So part of it will be its existing value plus something for the reward, okay? Now, let's say there's a huge reward, but we don't want to kind of give the reward entirely at each time, because that can lead to kind of learning too fast. Or if you give it an incentive, that incentive may be too much. And so we want to kind of temper that down a little bit, Okay, and so here comes the learning rate. Okay, whatever the penalty or reward that we want to give to that, to update the value, we want to multiply that by the learning rate. Okay, and so it's going to kind of this actually can be an optimal learning rate that will allow the bot to learn fast enough but not too quick, so you have to go back and forth. Okay, but anyway, there's a learning rate, and inside the parentheses I'm going to give the reward. Okay, and it comes from two major parts. Okay, the first part is the actual reward from this action. Okay, think about if this is the last action that you play and you win, right? There is the immediate reward from here. Okay, so that is, this reward is the immediate reward. But remember, there are also, I talk about this chain, right, of actions leading to the final reward. Okay, so, and there is a discount factor, like move 2 will lead to move 3, which will have the immediate reward of winning. And so move 2 should also have certain reward but discounted. Okay, so we are going to have a discount factor and then times, okay, the reward for move 3. Okay, but move 3 is actually, or is only part of the next state. Okay, perhaps the best action that you can do in the next state, they can lead to, that can actually win you the immediate reward. And so in the next state, there are still, of course, many different actions you can play, and so we need to find out perhaps there's a best, right? As long as you have a, in the next move you have a best option, okay, that can lead to win, that should be encouraged. Okay, and so what we're going to do is that we are going to, the next, okay, and if you can try to imagine this situation from the old state, you try to predict whether there is a future reward which is captured in the new Q value. Okay, because new Q value is the new state, okay, which is the old state after performing the action. Okay, I want to find out the maxed value from the new Q values. Okay, okay, so the max value and then minus the old Q values. Okay, action. Okay, so this is to calculate the difference of the reward, okay, minus the old Q value of the current. So this learning rate will allow you to calculate the difference and be able to kind of learn a bit at a time. Okay, so hopefully this makes sense. So with this, we have implemented the update function for this update Q value, okay, which is a very important function in this learning algorithm, in this Q learning. Okay, and the last function we're going to make is the move function. Okay, based on all this, we are going to create the last function for this reinforcement learning bot, and that's it for the class, and we'll be able to start using and training this bot after this. So bear with me, we are getting very close to the finish line for this lecture. Okay, so we are going to make a move. So define move self. Okay, and now first, in order to make a move, we need to call the select action and primarily, okay, and update the board. Okay, so we need the board, and the board should really come from the okay, so let me write this out, and then I'm going to kind of explain. So again, when we construct a bot, we're going to assign a game to it. Okay, and the game will come with the board, right? So this self.game.board will give you the board, current board that the bot is playing on. Okay, but because we are going to take advantage of all the NP functions, numpy, and so I use this np.array to convert the simple array to a numpy array. Okay, just to make it easier to manipulate computationally. And then the next step is we are going to actually get the current state based on the board. Okay, so we know the board which have all the 3x3 grid and O and X values on it, and then from it we can get the current state, the unique state, the current situation. Okay, and now based on the board we can also find out what available actions are. Okay, so we can call this let's say available val actions, right, equal to self dot get avail actions board, right? So we can find out what available actions are there, and then we can select an action from it. Okay, so we are going to select an action from the available actions. So select action, and if you look at the select action, it accepts two parameters. Okay, so state and available actions. Okay, so we pass the state to it and then available actions. Okay, so we get the state from here, available actions from here, we pass them to select action. Okay, and so as a return, it will return an action or the move. Okay, and now we can make the move, right? So now here is one thing. Before we proceed, remember the actions. I said I want to convert everything into one dimensional, only one number for each action because it's easier and more consistent. Okay, and now once we get the action, it's just one value. But in the end, we need, because it's 3x3 grid, in order to mark a cell, we need to tell it which row and which column. So we need to unpack the one-dimensional value index into two-dimensional, two values. Okay, so bear with me, and I'm going to do that right now. Okay, so this action, let me call it 1D. Okay, because it's one-dimensional, and then I'm going to obtain from the 1D a 2D action index. Okay, because we ravel it before, now let's unravel the index based on 1D and tell this function that we want to restore the one-dimensional index to a two-dimensional 3x3 matrix index. Okay, so that is what it's going to do, and so in the end this will give you two values. Okay, so actually and so based on this, okay, so action 2D will have row column indexes. Okay, so two index, and so with that we can call this self.game.move, right? And so let me make this kind of code easier, even though not the most efficient way to do the code. But okay, let's say I is for the row index and J is for the column index, right? So I is the first index from action 2D, and then J is the index the second index. Okay, so first index, second index, and I'm going to pass these two index to the move game.move function, which is going to move a step on the game board. Okay, and now when this is done, okay, we also need to change the state. Okay, and so we need to update the state because currently this state is the old state. Okay, we also need to kind of make sure we return the new state so that when we try to reward or penalize a move, we know the information. Okay, so in order to get the state, we need to also get the new board information, and this can be done by simply calling the game.self.game.board, and again we want to convert that into an numpy array, and then based on the numpy array we can obtain the state by calling the get state with this new board. Okay, so when we pass the new board to the get state, we can obtain the unique state based on the board situation. Okay, and then in the end, that's returned state, right? And this state, remember, this is actually the state return state, which is the old state. Okay, and then action, and then new state. Okay, three pieces of information that we'll ultimately need to update Q values. Okay, so we're going to, I think for this is action 1D. Okay, because we want to be consistent in the Q table is one dimensional for the Q values for each given state, and so we need to pass this action 1D. Okay, and then the and then new state. Okay, we return three values, and that's it. Okay, we can save this, and of course let's see if it works. There's probably bugs in the module here, but we still need to test and find out. Okay, so let's go back to the notebook, and I would like to start doing some code in here to import the module so that we have the but. Okay, so we have implemented in the buts, okay, in the same directory, the RL but, right? So this is the random but, and then we have the RL but. Okay, so that's from buts import RL but, right? And then let's create a game. Okay, for example, Tic Tac Toe. Okay, so we create the Tic Tac Toe game, and let's also create the but. Okay, so RL but, and pass the game to it. Now with RL but, we also need to tell it which player it's playing. Okay, so O. So we are going to, perhaps if you are going to play the but, you play X, and the but will play O. Okay, and let's assign some parameters. Okay, what are the parameters? If you go back, learning rate, we can have perhaps a slightly smaller. Actually, at this point, learning is not that important, so it's actually not learning yet. Okay, so we'll work on the learning side. Okay, because we still need to refigure out how much the reward is and things like that. So let's assign some values in there, and I would say still, and I will expand some of these values later when we actually work on the learning. Okay, but let's say 0.1 for the learning rate, 0.9 for the discount factor, 0.5 for the exploration or random moves. And now we can use game.set but to set this but to the game, okay? And then we can say game.display, and this is similar to the random but. We have the same interface, okay? And so let's run this, and looks like there are some issues. Okay, there are a couple of issues here. Let's fix some of the issues so that we can load this module properly. The first thing is this exploration. So because I passed the parameter as exploration, not x exploration rate. Okay, so change it to the same spelling. Okay, so exploration here. And then the second thing is down in the update q value function. And in the end, there is this old q values. There should be an s, okay, because it's from here, old q values. Okay, so make sure these two are fixed, and then save it. And then coming back to the machine learning notebook, make sure you also include this magic here, okay? So percent load underscore ext auto reload, and then percent auto reload 2, okay? And then I'm going to change this from bots import random bot to also reload the rl bot module as well, the class, okay? So if you have included these two, and whenever you make changes to the existing module, this will be able to reload, okay? Otherwise it will not recognize the new changes, okay? So make sure these two lines are here in there at the top, and then rerun this part, shift enter, okay? Now we have loaded the rl bot, okay? And then we can scroll down here, and we don't need it here anymore because we have already imported that module, okay? So we create the game, we create the rl bot, and then assign the bot to the game, and let's run it. Okay, so we have a bot, and we can play against that bot, okay, which is not intelligent at all at this point. Okay, it's going to make certain moves, but it's not really intelligent yet. Okay, you can play and you will realize that it's not really more capable than the random bot. Okay, so we need to make it learn. Okay, and so let's work on the learning or training portion, and that will be the last part of this tutorial, and then we can come back and play against the trained bot, and you will realize that the one that has been trained is much more capable. Okay, so what we are going to do in the next is to train the bot. And so again, let's double check we don't have numpy, so let me import numpy or numpy as np, and then I'm going to again create this game. Okay, so I'm going to repeat some of these here. Okay, let me do it here, and actually instead of set bot, I'm not going to set bot because we are not going to play the bot, but we are going to create two bots and make them play maybe 1,000 games, 10,000 games, and so that they will learn from each other. Let's give some names to these bots. Let me call one playing X as Simon, and then the other as Aleph. Okay, and Aleph will play O, Simon play X. Okay, and so I'm having the learning rate of so learning rate is 0.1, a small number. Let's change it to 0.2 maybe. I think 0.2 will make it learn faster. and then this point line is the discount. Okay, so the discount, the like the farther you are removed from the reward, the less award you will receive. Okay, so that is the discount factor, and then the last parameter is 0.5 exploration. So I make it 0.5 because we can say half of the time we'll let it explore, and the other half it will make an educated move based on past experiences. Okay, so that is our intuition, and this I think will give us some advantage. Obviously these are not the best, and we can certainly look into existing research to see what other parameters can even perform better, but for now they should be good enough. And a couple of things to keep track of the following. Okay, so we need to keep track of the players because they need to take turns. Okay, so there will be a player X and O. Okay, so two players, and then when they take turn, the bots also will be alternated, right? So because X is for Simon, so the first one is Simon, and then the second one is Aleph. Okay, and we also need to keep track of the O state for Simon and for Aleph. Okay, so initially just make them empty, that should be fine. And also the actions that has been performed by Simon and Aleph. Okay, so put 0, 0 in there as the initial values, and there are also going to be new states for Simon and for Aleph. Okay, so again, put two empty strings in there. Okay, they will be updated. Okay, once we start to train. And now let's define a function called train to start train the two parts. Because we want to reuse the train, maybe in the end we'll run it for 100 times, 10,000 times or more. Okay, so we need to reuse. And we are going to have this perhaps in session variable, okay, which will be true until it's not true if there's a winner. Okay, and then with the game, whenever we start a new training session, we start the game over. So game.start underscore over. Wait, actually this is also a function. I'm not sure if I fixed yet. So let me go back to the game.py. There is, okay, actually I haven't fixed this part. So originally we have this reset function, okay, but I actually wanted to create another function. Okay, so let's add a function to the game.py under the game Tic Tac Toe class and define as start over. Okay, self, and then I'm going to copy this piece of code under on reset click. Okay, because for now this piece of code can only be called when we click on the button, but we want the bot to be able to use it to start a game automatically without clicking the buttons. So what I'm going to cut it and paste it under the start over, and then I'm going to select and ship and tab. Okay, so to reduce the indentation. Okay, so this is start a new game. Okay, and then I'm going to under this on set on reset click, call this self start over. Okay, so this does not affect the existing code and implementation, but it gives us a function called start over so we can reuse it, okay, during training. Okay, so with this I think we do need to reload. Okay, so go back to the very beginning and reload this entire thing. And of course, we can, if you want, you can test it. Okay, I think you should continue to work with the random but. And now scroll down here, back to this train function. We now can call the game.startOver. And also there is the player index. Okay, play index, which is going to be because we use all these arrays, like 2-element arrays, to keep track of the current player, whether Simon, X, or state, action, new state. Okay, so this player index is going to be alternating between 0 and 1. Okay, for Simon and Aleph, Simon, Aleph. Okay, so the first we'll start with Simon, which is index 0, and then we are going to create a for loop. Okay, as long as this is in session. Okay, and until there's a winner. Okay, we'll continue to run, let them play. Okay, and we are going to call this bots. Okay, and then play index. Okay, dot move. Okay, so whichever the turn is, depending on whether it's 0 or 1, will alternate between Simon and Aleph and let them play. And we know when it plays, it would returns 3 values. Okay, 3 items: old state, action, and new state. Okay, so these 3 things will be returned. And then now we need to update these values to the 3 arrays here, so that we can keep track. Okay, so first is old states. Remember, this is the plural. Okay, old states, and then play idx index equal to old state singular. Okay, we're going to do the same thing for the new state. So I'm going to just copy, paste, change old to new. Okay, because they are almost identical. And then for the actions, I'm going to do also actions, play idx equal to action. Okay, action from here, want to assign to the action array here. Okay, these are keeping track of what's happening with the moves. Okay, now we need to check win, because it's important. If there's a win, we can reward, right? Or if there's an end, a draw. And so what we do is that we can use this game.board, okay, to check the win, and we convert that to an MP array. Okay, because we need to use it. Okay, in order to get the states and things like that. But for now, we also need to see if there's a winner. So winner equal to game.check win, right, to get the winner. And the winner, if it's if the winner is quote space quote or empty, okay, of course there's no winner. And so if the winner is not quote space quote, right, it's either an X or an O, there's a winner. Okay, so in this case, in session is false, because the game is done. There's a winner already. Okay, so if there's a winner, depending on who the winner is, we want to update. We want to, if for example Simon wins, if X wins, we want to reward Simon and penalize Aleph, right? So that is the idea. So here, because they are in an array of 2 elements, so we can use a loop for I in range 2. Okay, and so if players I, okay, equal to winner, right? If it's a winner, we want to reward that. So in that case, bots I, which corresponds to player I. Okay, so Simon plays X. Okay, so if X is a winner, then we award Simon. Okay, so bots I, we can update Q values, old states I, right? So we basically pass the old state for the I player, okay, either Simon or Aleph, the I, the action. And if the win, let's say I'm just going to arbitrarily say it's going to be 10. It's 1 or 10 or 100, doesn't really matter, because this is, for now, the only reward. If we have other rewards, we need to kind of have a better strategy in terms of how much for each one, okay? But for now, this is the only reward, so you can give any number. They will not affect the result. Okay, so state, old state, action, new state. Okay, that is the reward. If it's not the winner, that means, okay, that is the loser, right? So whoever loses will receive a penalty, and the function will actually be rather similar. Okay, so we'll copy paste here, but instead of positive 10, we're going to use minus 10 to penalize the bot. Okay, so we'll know they will get updated with those Q values, and they will know, okay, not to play those in a sense in the future, right? Because if they lead to penalties, they will not be selected, right? The scores will be lower, and they won't get selected in the future, hopefully. And then, so else if bots, okay, play. So if there's a winner, right? This is the situation when the winner is not empty. But what if the winner is empty? Is empty? There's no winner, but the game is already, the board is already full. Okay, so there is a possibility, right? So remember, we create this board is full function. Okay, so we can call it to see if it's full. If it's full, in session is also false, because if it's full, it's done. We need to start new game. Okay, so in that case, it's done. We change this to false, and in the end, we should alternate, right? We should alternate the term, okay, between 0 and 1, which is or x and o. Okay, so o. So how do we do that? We basically say if it's 1, if the current value, if the current play index, let's see, is 0. Okay, so if it's 0, we change to 1, and if it's 1, we change to 0. Okay, so basically alternates. This is to say, if it's currently 0, we make it 1. Otherwise, we make it 0. Okay, so this will alternate between 0 and 1. And I think that's pretty much it. Okay, so we can run this, okay, to load the function. But now we need to train. Okay, so how do we train? I'm going to just do this part rather quickly, because I want to run this for a number of times and see if the bot can actually play something good. Okay, but I'm going to also keep track of time, of how long it takes to do the training. Okay, so I'm going to do perhaps 10,000 runs. Okay, and in each run I'm going to train it. Okay, so each train is a new game. Okay, and so here, and then I'm going to have also an end time. Okay, so end time, and then time elapsed equal to cos end time minus start time. I do want to convert this to milliseconds so that we know exactly how long it takes, and so we can say it takes perhaps so elapsed milliseconds to train. Okay, to train. In this case, it's Simon and Aleph. Okay, so let's run it. Actually, there's a problem. Oh, okay. Train. Okay, let's double check. So new state. Oh, Q values. So again, I have a bug in the update Q values. So I misspell. Okay, so Q values, double check. Okay, save it, and then we need to. This problem is actually not here, but in the module. So let's reload the module back at the top. Reload the module, and then we can run it again. Run this train module again. Run this part again, and so it's training. Okay, so the module I was running was taking much longer, so I had another module that I developed to run much faster training, and I'm going to quickly show you the result here. Okay, so this is the same training actually that runs 10,000 times, and with the parameters learning rate I believe is 0.2 and discount factor 0.9 and then exploration 0.5. Okay, so the same training, and to train two bots. One is Simon, who plays X, and Aleph, who plays O. Okay, so because Aleph plays O, okay, I want to use the train Aleph because she knows O, and I'm going to, as a human, I'm going to play X, right? So let's create this real game, okay, to construct a tic-tac-toe and call it a real game. And then I'm going to run the display the game, and then the real game I'm going to set bot, okay, Aleph, because Aleph has been trained. Okay, do not reconstruct Aleph because it has been trained. If you reconstruct it, it's going to lose memory. And so just use the existing Aleph from the above training and set it as the bot for the real game. And I'm going to adjust the parameters for Aleph because, you know, the ones that we use for training are good for training, but they are not necessarily best for playing. For example, especially for the exploration. Right now, what I want to do is to have 0% exploration. So no exploration, no random move at all, but purely based on what Aleph has learned in the training process, in the 10,000 games that she has played. Okay, and so I set the parameters, but the key value here is really 0 for exploration. And then I also change call Aleph.change game to real game, okay, which is the current game, okay, which I'm going to play too. Okay, so let's run this, and this is the game. Again, as usual, I'm going to play X. So let me play, okay, and then if I play here, hopefully Aleph will know to block me. It does. That's good. Let me try here. Okay, it does block me on the other side. So looks like Aleph has developed some intelligence to block me. Okay, and so in the end, this is a tie. You can try it, and my son actually played, and he figured out there's a way to kind of beat Aleph easily, and with more training, perhaps that bug in the in this current version can also get fixed, okay, by learning. But this is our version of reinforcement learning applied to the game of tic-tac-toe. Okay, Even though this is only 3 by 3, it actually takes a lot still to learn. Think about there are almost 20,000 permutations of this simple game board, and it takes 10,000 games for Alex to actually play um, decently. Okay, so try it and join it. And next time, I think we are going to kind of optimize the code and this module for reinforcement learning so we can train actually faster. I already have that module there for faster training, and but we're going to talk more about that next time. So it's already enough for this for the video today, and I'm going to see you in the next one, and things will get even more exciting, I hope. See you.